Hi everyone. I'm Mou-Yung Liao from Taiwan, and this is a topic I would like to share today. This is my first time attending and presenting in ICCF, and I feel great honor to be here. I would like to first quickly introduce myself. I was majored in mechanical engineering in the National Taiwan University under Dr. Bingjun Huang's advice. And I was once a thermal engineer in the server industry. But currently, I became member of Dr. Bingjun Huang's research team again in 2 years ago. As Dr. Bingjun Huang mentioned before, we had some progress in identifying isotope evidence in our cavitation-induced linear reactor test recent years. And you can check the publications for more details. At the same time, we were also working on the performance improvement of our reactors. And here I come to share a brief introduction of our research. So the main subject I would like to talk about today is called the linear flow network analysis, aka LFNA method, which has been used for decades on applications such as engine, cryo cooler, and also the waste heat recovery. It helps simplify the complicated thermal-acoustic effect and also the oscillation problem in fluid flow. Also, it gives good guidelines for our quick design of components. We consider it a better strategy with this method instead of using costly and time-consuming CFD simulation. And most importantly, it enables us to scale up the design. We have realized that when it comes to an industrial power plant, a single component of our reactor could be as large as a car, like this picture shows. The LFNA method here is basically the fundamental for our future development. So today I would like to briefly share two applications of LFNA in our reactor design. And here's the outline. Okay, so first one is the abnormal temperature rise effect our team found previously in some of our tests. And it's an unreasonable phenomenon since it violates the principle of thermodynamics intuitively. At first, we thought the temperature rise was merely caused by the excess heat, but somehow we found some reactors without excess heat production can also have similar temperature rise. Therefore, we try to study more carefully on this effect and try to explain in classical knowledge of fluid mechanics and thermodynamics with our LFNA method. So this page shows a recent example that has been tested last year in our laboratory. The series of JT5 reactor tests showed measured temperature increase around a few degrees Celsius. It's not a large increase, but valid enough to identify. We believe that this temperature rise effect is similar to the flow oscillation happened in a pulse tube of cryo cooler use. Therefore, we try to use the LFNA together with the pulse tube theory point of view to explain this abnormal effect. So by the way, since we also found some correlations in several types of our other reactors, that the greater the thermal impact, the better COP we could get. The idea of increasing the thermal impact in our reactor through the reinforcement of the abnormal temperature rise effect has quickly come to our mind. According to the extrapolation from our experiences, COP could be increased by 10% per every 20 degrees Celsius temperature rise. If the temperature rise is large enough, we might be able to improve the COP without extra input power or other extra effort. So start from the linear flow network model of pulse tube, referring to paper 1 here. Basically, LFNA utilized electric circuit analogy together with the perturbation theory to solve a fluid mechanic problem. In other words, the pressure perturbation is analogized to voltage, and the mass flow rate here, the perturbation of mass flow rate is referred to current. And we reorganize the fluid property into components like resistance, inductance, and capacitance in the electric circuits. To make the long story short, with this network model, we are able to calculate the parameters we need for the circuit analysis based on the given input condition. And eventually, we can solve the output oscillation of pressure, mass flow rate, and also the temperature. Then with the energy balance analysis, we are able to solve the temperature difference between both ends of a pulse tube. In addition to the pulse tube, there are other fluidic components in our system. Like, for example, in our JT5 reactor, it consists of orifice or series of orifice, and also a resonant chamber, which are corresponding to pure resistance and capacitance component, respectively. By putting everything mentioned above together, we'll get an electrical analogized network model, and we are able to solve the problem with the general circuit analysis, somehow the Kirchhoff laws. So this page shows the flow chart to solve the output temperature rise across the reactor based on the derivations in the previous slides. So the results show that only excitations with some appropriate frequencies will cause the temperature rise. The simulation results shown here are in the same order with our practical experiences. Moreover, the right result here shows that an output temperature rise nearly 100 degrees Celsius, or it can go even higher, can be achieved under specific conditions. So we need a proper frequency for this, and also it depends on the location in the pulse tube. And here's my second topic I would like to share is when a flow passes through a mounted cavity, it has the opportunity to create sustainable oscillation. It's called a self-resonating jet, SRJ reactor design. So the research right here shows a reinforcement of high-pressure cavitation jet flow with additional cavity mounted to a nozzle. So under different flow velocity, different frequency characteristics in the cavity were found. Two kinds of flow oscillation modes are distinguished on this spectrogram. That is the hydrodynamic modes, and another is the geometry resonance mode. So the frequency spectrum here shows that when these two kinds of modes coincide with each other, it results in enhancement of the cavitation. So for the hydrodynamic mode oscillation frequencies, it is associated with the shedding vortex and also a positive feedback mechanism of standing wave generated inside the cavity. And this can be evaluated through the so-called Rossiter formula, which requires the free stream Mach number and two empirical coefficients, alpha and kappa, right here, for different cases. And for the geometry resonant mode, we can solve the frequency based on the reactor geometry analytically with our LFNA method. Besides, there's a tricky part here I would like to mention, is that we will need the wave velocity, in other words, the speed of sound in the working fluid to calculate parameters such as the capacitance and also the mentioned Mach number. Some other researchers indicated that the sound of speed in two-phase flow is highly affected by the void fraction, which is the gas volume versus the liquid volume. And we can estimate the speed of sound accordingly. However, direct measurement of case by case is still believed more reliable for us. So here shows the flow chart to check the coupling between the vortex shedding frequency and the geometry resonant frequency of our SRJ reactor. Okay. So we have designed so far we have designed three kinds of SRJ reactor, referring to the previous study, SRJ 5, 6, and 7 right here. So those dimensions were based on the convenience for us to build in our lab. But among these existing designs, we have it's already feasible for us to create amplified pressure wave for more than 1,000 times, which is the SRJ6 shown right here. Although we still need the proper excitation for this amplification to occur. And here shows a scenario of a scale-up reactor when implemented to megawatt level power plants. Both cases have similar order of magnitude. These two cases both have similar order of magnitude of resonance frequency, but there are considerable differences in pressure amplification, which implies that there's no completely positive correlation between the resonance frequency and the pressure amplification. This also means that a reactor with larger dimension may lead to a lower resonance frequency, but relatively high amplification. The concept, so the concept shown in this page is to tell that with assistance of amplified pressure wave in our reactors, we are expecting to enhance the cavitation intensity, but also the number of cavitation events with aid of strong pressure oscillation, whether in bulk liquid or scattered droplets inside our reactor. And moreover, increasing the probability for LENR to occur. This will be further verified with the following consistent COP measurement and also the isotope analysis of our working fluid sample in our reactors. So far, we have built a test platform for this type of SRJ reactor validation. Also, we expect 2 target sites to trigger LENR, which make SRJ into a 2-stage reactor. We have already done some of the preliminary tests, while the system operation and control are still ongoing. And further is investigation of the LENR evidence, such as isotope analysis of our water sample with mass spectrometry is also under planning. So here's my conclusion. I have 3 main points for you to take away today. First one, the abnormal temperature rise effect and also the flow resonance phenomenon in cavitation-induced LENR reactor were investigated based on the linear flow network analysis, LFNA method. And the second point is the analysis results show an output temperature rise nearly 100 degrees Celsius or even higher is feasible for us, which could be implemented to increase performance with enhanced thermal impact. And the third point is simulation results shows a larger than 1,000 times pressure amplification can be achieved with appropriate design and flow conditions to boost cavitation and to further improve LENR to occur. And here's my references. And that's all from me today. Thank you very much for your listening.
Okay, thank you, Mou-Yung. Any question?
Okay.
Thanks for your presentation. I just wanted to ask, have you considered the, it looks like you've got a pressure-dependent compressibility. We know that in compressible gases, for example, if you have a rotating high vorticity flow, you can have a temperature gradient from inside to out. It looks like potentially you've got some amount of your temperature increase from a similar type of phenomenon. Have you considered that at all? And I think you should be able to model it and then look at if there's an excess over that amount.
You mean the temperature gradients? Do we consider this in our reactors?
Yeah, and in a rotating like a Rank-Hilsch flow, like a vortex, it'll be hot on the outside and cold on the inside. And that's for a compressible gas. Both of your fluid equations for both the laminar and turbulent, it assumes it's incompressible.
No,
But
we have considered the laminar and the turbulent in our model.
yeah, but they both are assuming that it's an incompressible fluid. But when you've got these microbubbles, you're adding this.
We have considered both compressible case and incompressible case in our flow chart. Yes.
Yeah. Okay.
Thank you.
Thank you very much. Wonderful presentations there by my friend. I had a very interesting conversation with Vlad Jigolov about vortex cavitation reactors last night, and they found that only when you had a very, very long pipe, which was in your original reactors, did they see excess heat. If they just used a calorimeter from the cavitator, they did not see any excess heat. So the idea is that you set up a vortex and you keep it running. Are you considering doing experiments with different lengths of pipes in your heat exchanger?
Yeah, I think we have considered this, but it's all based on the design, the calculation. So yeah, trying different kind of lenses is possible for us.
Okay, secondly, the Kladoff patent notes that when he added a 5% aluminosilicate suspension, the COP went from the kind of COPs that you and Binja and Huang are seeing up to about 11.7. So from 70 kilowatts in, they produced 760 kilowatts of thermal heat. This was obviously in the turn of the last millennium. So I recommend that you use aluminosilicate, because I have seen in analysis of your systems that it's sometimes using the copper pipe as the fuel source, as well as the water. I would suggest giving it something much cheaper to work with, aluminosilicate, as was done by Kladoff, producing a COP of 11.7.
Yeah, I think we can consider this.
Thank you very much. Thank you very much for your work.
Thank you, Bob.
Okay, Conrad.
I want to ask you about, your model is very nice, but it's an analytical model. Have you checked it, with some CFD calculations? Three-dimensional, it is...
Well, I think we don't have the calculating power right now. So, and also if we use CFD, for us, it may take a very long time to know the results. So we try to use this kind of simplified design tool instead.
Because this kind of calculations are also important not only for fusion but also for fission reactors. New types of reactors are needed, and the people use their CFD mainly. Because of it is very time consuming. I agree. But it's, I think, necessary because you can compare the results very exactly.
Yeah, maybe in the future, if we need to optimize our design, then maybe we'll consider using the CFD instead.
But I think this resonance behavior is really interesting for different fields. If you study the flow. Yeah. Thank you very much for your presentation.
Thank you.
Okay, so any other questions? Not seem to be the case. So let's thank the speaker again.
Thank you very much.